Hi, good morning. Thanks a lot to Ajith and others, other organizers for inviting me here and for this opportunity to be present at the Bala Fest. So what I'm going to do today is to give you some, because in keeping with the title of this conference, I'd like to give you some things that are happening now and which may have an impact in some near future analysis of CBC sources. So just to get the groundwork done, so templated match filtering pipelines are basically the mainstay of the way in which CBC data analysis is carried out. And almost all the CBC data analysis pipelines today are based on template-based match filtering. There are one or two new experimental pipelines that are coming up which are slightly different, but here we are going to entirely base this on the template-based match filtering. And the groundwork was laid down by a series of papers that appeared from 91 to 94, where basically the idea is that the detector is composed of the noise and a signal which arrives at some time t, which means that at some time ta, its instantaneous frequency hits the lower end of the bandwidth of the detector. And you model each of this of the noise at every instant as a zero mean random variable, and you associate a power spectral density with this of the noise. And you define a correlator of this detector output. This is in the frequency domain with some filter Q. And you can show that the signal to noise ratio, which is defined in this way, using the mean and the variance of this correlator, can be shown to be maximized for a match filter where Q has this very specific form of the signal divided by, so this is the over-whitened signal, basically, in our parlance. So if you look at this object, this is nothing but the dot product of these two as you advance this object in time. So that's a small, so I took the liberty of making a small kind of obvious animation just to show that how it works. So basically, when you maximize that correlator over phase, you end up with an expression like this. So this is the whitened data, and this is the whitened template, and you basically advance this template in time, and you calculate the dot product along the way. So that's what you do, and this is how it works. So this is the data, the whitened data around the GW150914 event. And this is the template that is moving in steps of delta t, and as it hits the point in time where there is a hidden signal somewhere here, you see that this detection statistic hits a maximum. And you put a threshold on it and you do other things with it, of course, and it's too long a process to be described here, but I'll just highlight some salient features. For instance, this SNR or this detection statistic now, you see picks up a timestamp, depending on how far you have to advance it with respect to some timestamp, which you call 0 in this case. And it also picks up the tag on the masses and spins of the template, which was used to actually carry this operation out. And what you end up having is basically a template bank, which is a collection of these templates. And I'd like to show you that a lot of effort has gone into placing these template banks. For instance, it started with the early efforts of placing geometrical banks, which Thomas Cochlear, Stas Babak, and Satya put in a lot of effort in the early days, and then followed by a stochastic template placement algorithm, which was again due to Ian Harry, Bruce, and Satya. And then that was improved upon by some bells and whistles, including a variable starting frequency, which in order to tackle very large template banks, especially for advanced LIGO detectors. So the current state of the art is a hybrid geometric stochastic bank, which improves upon this idea by Canton and Harry. And it combines both these ideas by realizing that if you have a n-dimensional space. It's based that the problem of template bank placement is essentially a sphere covering problem, and you can use an AN star lattice because it provides you with the thinnest covering. And in fact, that bank is now being used in the O3 online and offline searches. This is just to show you that this current bank is at least as good in covering the parameter space as the O2 bank, which was used earlier. Now, coming to the problem of template banks, as the detectors get more sensitive, as their bandwidths increase, and as we expand our horizons to search for more spinning, higher masses. Actually, higher masses don't matter, but anyway, we run into the problem of several 100,000 templates in the bank, and computational time of our searches are directly scaled with the size of the template bank. So a wonderful idea came out in 2010 where you could stack all the templates in this fashion, and you could try to find a suitable set of bases to span these templates. And the fact that these templates are highly correlated with each other also implies that this matrix is a rank deficient matrix, which means that once we have expanded each of these rows into a suitable basis, we can actually represent this approximately by its low rank approximation. And when you represent this matrix by a low rank approximation, of course, there are errors in it, but you try to control it by comparing the total energy of the approximate matrix with the actual template bank matrix. But these are extremely wasteful methods because what you do is you have a huge template bank, and ideally what you would do is you would break it down. For instance, you could do a SVD decomposition to find the ideal basis vectors. But then because only a very low rank would suffice, you'd end up discarding almost 80 to 90% of the singular values and singular vectors. And of course, once you've done that, you have control on the reconstruction accuracy and so on. And these basis vectors would then become surrogate templates with which you would filter the data. And once you have this, you can reconstruct the detection statistic by multiplying it with this large coefficient matrix. And there are different pieces to this. It turns out that now that you've broken it up into a low rank matrix, the filtering cost becomes negligible. You don't even, it becomes negligible in comparison to the reconstruction cost. So one idea that has been put forward only recently is to use random projections in order to solve this problem. So what random projection is to represent vectors in a very high dimensional space and project them into a low dimensional space such that the distortions of these vectors when you project them can be controlled suitably. And these projection operators are just drawn. These are just vectors drawn from, this is one example, but there can be several examples. There can be several ways of, constructing these projection operators. And they have these nice properties that their distortions can be controlled by choosing what dimensional space that you want to basically, and they have these nice properties that pairwise distances are preserved to reasonably good accuracy. So that was used in order to, so we showed that that can be used, in fact, to do this decomposition of this very large template bank, not in the SVD fashion, but using random projections and taking a QR decomposition. And that can be found here, but there are, of recent, we have made several other improvements on this. So for instance, we can control the low rank at a specified acceptable error. For instance, when we do the analysis, we don't really care what rank you're using. We are more worried about controlling or having a control on the absolute error that we make when we are doing this operation. So it's basically asking the question in a reverse way. Able to deal with various banks, and I'll show you that we are also able to do the SNR reconstruction costs to some extent. So this is some work that is going on. So here is one last slide that I want to show you, and this is a message that I want you to take this from this plot. So once you have done a decomposition in some orthonormal basis, this red dashed line is basically the filtering cost of the data with the basis functions. And this blue line is basically the cost of the reconstruction. And you can see that when you do an SVD kind of a decomposition, and this is still unsolved. I mean, we really don't know how to control this cost. So this is an open problem. And one of the ways by which this can be controlled is to divide the template bank and split it into many sub-banks, and that we can have a good handle on this very dominant reconstruction cost. And this is basically at the heart of the GstLAL pipeline, basically. And the reason is this. Next, I want to show you some stuff that is being developed very, very rapidly. And this is everybody's favorite object for bashing. Basically, this is machine learning, because we don't really trust these results very well, or we don't understand how these work very well. But regardless, they are coming thick and fast, and we must wake up to that. So for instance, there's a lot of activity, which I will show you some papers where there's machine learning is being used for denoising gravitational wave strain data. So basically, the idea is that you have a corrupted detector noise, some data X, which contains signal Y and some noise. And the objective is to learn a function or even handcraft such a function, which maps a noisy data to a clean signal. So basically, you want to get from X to Y. And there are basically two kinds of initiatives under this. So basically, there are some regressive models, which are data dependent. For instance, denoising autoencoders are being used. And there are some generative models, for instance, wavenets and GANs, everybody's favorite toy these days, for doing this. So I just want to highlight this. I don't want to get into the nitty-gritty details of all these various work. I just wanted to highlight that there's a growing body of work, and very soon I think they will be very useful in at least helping us with the CBC data analysis. I don't anticipate that they will take over the way we do data analysis in CBC anytime soon, but we must be mindful of these kind of technologies that are being developed. In particular, very interesting recurrent autoencoders where one uses sequence-to-sequence networks, and wavenets, where for signals across the binary black hole parameter space with signal-to-noise ratio greater than 12 have been denoised with an overlap greater than 0.97. So we are just getting there. So if you go through some of these papers, there are some ideas how this can, how the noise-free time series produced by these kind of denoisers can be combined to get accelerated astrophysical parameter estimation from these kind of work. So just to give you a visual of what these guys can do. So for instance, here we are trying to denoise a spinning binary black hole signal at SNR 7. So this is the whitened data. And here, one on top of the other, you see the injected and the denoised signal. And here is a zoom in of what is happening in the last few cycles, basically. Pardon this, this is mislabeled. These are just samples. So you can see that these are, these reconstructions are better than 98% accuracy. But of course, more work needs to be done. For instance, people have tried to denoise the GW catalog events. For instance, this is the 150914 event. This is another event, and you can see that these overlaps are better than 99%. So there's a lot of promise in these kind of searches. And so one of the, sorry? Sorry? Yeah. So, so for instance, although you may or may not trust the reconstructed signals very well at this point, but what we are, one of the things that we are trying to do is to calculate time delays across detectors. And these time delays are very well reconstructed from these denoised signals, which could be potentially used for rapid sky localization, even without having done the analysis. So, and so we could go, one of the ways that I see this is that this could trigger templated searches coming from the other direction. So, for instance, here is a plot where you see these are 3 different models. And the y-axis is some measure of the time delay measurement accuracy, and the x-axis is the SNR. And you see at SNR 6 and above, these are very early results, but still they show quite a good potential for calculating the time delays. Finally, I'd like to touch upon a topic that is closer to my domain. So this is the efforts that are going on to detect higher order modes of CBC signals. As you know, the signals are, from CBC sources, if they are face-on and so on, they're dominated by the quadrupole 2-2 mode, and higher modes are weaker by comparison. Of course, there are many considerations, including inclination angles, the mass ratios, and so on. And also the fact that in advanced detectors, we expect to observe many such CBC events. The idea is that can we combine the signals from multiple events to enhance the higher order modes in the data? And of course, there are a few efforts that that I'm going to just very quickly flash through, which leads to coherent and sometimes semi-coherent stacking. And of course, you realize that this is easy in the post-merger and the ring-down part of the signal, where the ring-down frequencies are constant in time. And of course, and they only depend on the black hole intrinsic parameters. But it is harder to stack these higher order modes in the inspiral domain, as the frequency rapidly changes in time. And of course, that time-dependent frequency also depends on the intrinsic parameter of the source. So here is an example where highlighting some recent work by these authors, where you see the ring-down mode is basically, all the ring-down modes are at a constant frequency. And so what you do is you start with the base event, and you rescale all the other signals so that the target mode in each of them has pretty much the same frequency. And then you sum the waveforms so that they add up constructively. It's a very interesting idea, I think, but this has not been demonstrated in data. And of course, there are some generic practical issues which are not very clear how to implement it. For instance, there are issues of how to isolate the ring down. Of course, there are many thoughts on that. How to create optimal residual data. So when you're trying to stack this out, in order not to get completely overburdened by the 2-2 mode, you want to get rid of that. So it is not very clear how to optimally calculate the residual, which is the 2-2 mode free data. But these are generic problems. Any stacking method which comes up will have these generic problems. So here is a plot which shows some measure of the presence of higher order modes versus, this is a histogram. For instance, these yellow bins are for individual events. So it is possible that you have a very, a golden event which has a very high power in the subdominant modes. But on an average, this distribution, this is the distribution of this detection measure. Whereas if you stack some of these events, so there's an algorithm that goes behind stacking how many in each of these bins, you see that this whole distribution shifts to the right. So on an average, you get a stronger signal for the presence of higher order modes. Similar work has been done in the time frequency domain by these authors, where they attempt to stack all the signal modes. Here you would realize that you can only enhance one particular mode of your choice. Whereas these guys, try to improve upon them, but in the process, it leads to actually a semi-coherent stacking. It's not a coherent stacking at all. this is my last slide, basically. So we've been trying to work on this problem from the inspiral side, where you can see that you can add up the energy along time frequency trajectories scaled by a parameter alpha, which scales these trajectories with respect to the 2-2 mode. And in doing so, you can coherently stack all the higher order modes. So for instance, here is a plot which shows the stacked energy as a function of this parameter alpha. And you see for different systems, the energy basically comes and sits exactly at the right alpha. And so this uses a time frequency representation of these signals, and here's an example of that. So I'll end with some concluding remarks. So for instance, in the coming days, I think machine learning based algorithms will impact many aspects of CBC searches. For instance, not only will be, I would like to see them used in the denoising, detection, coincidence, sky localization, in fact, using calculation of the significance of events. But however, this development is very scattered and it's not very well organized of now, and some efforts in that direction I think would be very useful. There is some promise to in the detection of higher order modes by coherently stacking multiple events, but they can be used to test GR and devise many consistency tests. Several of them are already underway. And one can possibly use randomized linear algebra in CBC searches, and which could one day be useful for faster PE studies. That's all I have. Thank you very much.
Okay. Thank you, Anand. Any questions? Yeah, Sugant.
Yeah, so I have a comment and maybe a question. The comment is on this coherent stacking. For coherent stacking, you have to get I presume, the mass of the system reasonably accurately. Otherwise, the different waveforms will shift with respect to each other. And so it won't be a constructive construction. So why not stack in power? Maybe this idea will work when the signal to noise ratio is very high, the coherent stacking. But the power stacking is going to be more immune to these mass errors.
So by power stacking, you mean, so I'll just get back to this slide. So this is basically the power along the pixels. You are basically, this is just a Riemann sum along the pixels, and you're just stacking over alpha. So this is actually power stacking. So you're stacking the power along the alpha parameter.
So you're not necessarily rooting for doing coherent stacking as, for example...
So not in time or frequency, but you find a parameter over which the power stacks coherently.
Okay. The question is about the reconstruction of the waveform. When we do reconstruction using multi-detectors, using something like coherent wave burst, I would say it is impressive because it is not using a signal model.
Yes.
But if you're using a signal model for your reconstruction, what is it that is so big deal about it?
Quick. I think that is at least this point, all the focus of all the papers which talk about reconstruction or denoising, the focus is on, that it can be done in a streaming way in almost no cost at all. And as you discover more events, you you can train, the model better and better. But I think, as I said, it's not very well formulated exactly as to, what should be the aim of these kind of techniques vis-a-vis the ones that are very well established already.
And you demonstrated for a single detector, not using...
Yes,
okay,
this is for a single detector.
Any other question? Yeah, Tarun.
Yeah, if you go to your last slide, I just wanted to get a sense of which are the areas that are now represented in the Indian group in India, and which could grow, and what are your thoughts on what are the
This
areas?
is a very narrow selection of kind of problems that that are interesting to me.
Okay.
But
so these are all
areas. There are a lot of interested groups I know who are working on different aspects of applications of various kind of machine learning for glitch detection and classification of glitches, mostly in that area. And also, at least in my group, we are very interested in applying this for other aspects of CBC searches. So this is, I think, this is one area which is going to grow, in my opinion. But we need to sit down and have a very clear idea of where we want to take it. Right now, it's like a few scattered groups trying to do something on their own without much coordination.
Thanks.
Yeah.
Yeah, so just following on from that, so there's 3 separate groups have shown that deep searches for binary black holes produce exactly the same sensitivity as match filtering searches. Why? Oh, sorry. Why do you think that hasn't taken off yet? Why are people not doing it? It's just the same and significantly easier and quicker.
Yeah, this is a sociology question more than a scientific question. I think it's just a matter of time. Once they are demonstrated, over large real data sets, for instance, in many machine learning projects, you have very standardized data sets, and there are a bunch of tests that one agrees beforehand in order to, standardize the whole procedure. That has not happened yet in gravity waves. So I think that is going to happen. That's the way it should happen, so that they are more acceptable, to the wider community. A lot of it is basically a lot of many people view this as a black box without realizing what is, what can happen and things like that. So.
Yeah, that's one. It's on. Yeah, I agree that. But I think it's a false impression that it's a black box. The people that looked at those 3 separate groups, I'm one of those groups. We know exactly what's going on. Maybe it's our responsibility to explain it a little bit better, but it shouldn't be viewed as magic.
Absolutely. So for that, in fact, the first papers that were written, I think if you've been following them, you'd find that they were very, very, written completely in a language which was not accessible to the gravity wave community. But they were rewritten in a way, once they got some feedback, in a way that other people in the community could understand. So I think that more of that is going to happen. And these are just very, very early days, but very promising nevertheless.
Yeah, quick question on the stacking method again. So I didn't quite get the scope of the goals. So for example, you only have, if you show there is something, you only have a sum of modes, but you don't know the individual modes from each event. So how would you use that, for example, for tests of GR or something? Or is it even in the scope of this method, or is it just to show there is something?
Yeah, so it's a long answer. So, maybe I can catch you outside and give you my initial ideas about how one can go about it. But yeah, it's not very clear. It's not very crystal clear of how it would go about, but we think that there is a lot of promise. One can actually do something.
I have one question on the thing. It's about that, have these things been tried out in real noise? Or
Which one?
This kind of methods, the ones you showed.
This?
No, last.
Stacking? No. These are just ideas at this point.
Okay. They have not been.
No.
But what are you saying something about machine learning? Yeah.
So, Anand, there's this really interesting new body of work by the IAS group on trying out this problem in a very different perspective by essentially digging out all the non-Gaussianities and getting the Gaussian background and etc. So it seems to be like a new philosophy, and there are interesting techniques I understand borrowed from the CMB analysis, etc. So what are your thoughts on, for example, absorbing some of these ideas to the CMB, so the CBC analysis?
Right. So I think these might be useful for unearthing, like sub-threshold or near-threshold events, and then triggering a search around it to kind of unearth those. That is at least, as far as I can say, I think these techniques will be useful there. But I don't think they can replace the well-established analysis, especially with latencies coming down every month almost with more, improved pipelines. I don't think they can replace, but they can, trigger sub-threshold searches. That would be a very nice place for these techniques.
So let's move on to the next talk. I think we are.
Yeah.
So thank Anand. A very nice talk.